So, the gradient and actually 3 subtopics here. Gradient, again, by gradient I mean gradient vector or tangent plane, normal line. I think you have 1 or 2 assignment in your homework. The last 1 or 2 are like that. So we're going to say the following: given well, that's what I said. If this is generalization, if you have a level curve, it will be a line. If you have a surface, you have one tangent line, you have infinitely many tangent lines. It will be true to all the tangent line at this particular point. That's what makes it tangent plane. So I can, you know what, I can do slash line slash plane to a surface. So I'll do curve. I'll generalize it and I'll say to the level curve slash surface. This particular proof was given for a surface because it was function of x, y, and z. But you can drop the z and it becomes a curve and it becomes a line. All right? All right, so given a surface f of x, y, z equals k, the surface level. At some point, x sub 0, y sub 0, z sub 0, then the tangent plane so the tangent plane to the surface will be given by del f del x minus x sub 0 plus del f del y, y minus y sub 0 plus del f del z, z minus z sub 0, and all of it equals 0. Remember, equation of a plane where you have, well, let me write it. Recall that a plane is defined by the normal vector, by its corresponding normal vector at a point. So recall that in general, the equation of a surface, the equation of a tangent plane, of a plane, actually, of any plane, is given by its directional number the directional number is actually the component ABC. So let me write it this way. Direction number that are the component of the normal vector ABC at a point x sub 0, y sub 0, z sub 0. So the general equation of a plane is a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equals 0. Okay, so you can see that in this case the a, b, c, the direction number of this plane are substituted by the component of the gradient vector. Okay. So what it does, it's easier to come up with equation of tangent plane than before. Before we were looking for a normal vector and all of that. Now, if we have a function, we take the gradient and say, okay, those are the direction numbers. So, so the directional numbers A, B, C are replaced by the component of the gradient vector. We need slight modification if you have a function of two variables only. Okay? What happens if you don't have del f del z? Well, that's even simpler, because if we have, so this will be, let's say 1, and let's do another point, given a curve, a level curve, f of xy in this case equals k. Okay, we let z equals f of xy, and we create a function f, uppercase f. F of x, y, z, and what we'll do, we'll take, we'll write f of x, y minus z. So f of x, y, z will be f of x, y, the function that describe the level curve, minus z, like so. Okay. And of course this equal to 0, because f of x, y equals z, or f of x, y minus z equals 0. And now we differentiate, or we'll find the gradient here, and we're going to say that the gradient of this new function f of x, y, z will be, if you differentiate, it will be the derivative component of f of x, y. So this will be del f del x in the I direction plus del f del y in the j direction, and the derivative of del f del z will be simply -1, right? So so it's simply -1 in the k direction. Like so. Okay. Remember, we take the derivative of uppercase f, but as you take the derivative, the partial derivative, well, you have only x and y are present only right here. So the derivative del f uppercase x is really the del f lowercase del x, del f lowercase del y, and then del f uppercase del z is simply -1. Make sense? And of course the derivative of 0 is 0. Actually we're talking about the gradient, so we don't have to worry about what it is. So we have in a vector component, we're going to write it as del f, del x, comma, del f, del y, and then -1. So, so what happened to the tangent plane? If you place this right here, knowing that here you have -1, the left of z is -1, then you have the same two, the first two expressions are the same, and here you have -1 times z minus z sub 0. And indeed, that's the case. So for two variable function, you'll have this component of the gradient times x minus x sub 0, then the j component of the gradient, the left del y, times y minus y sub 0, and del f del z is -1, so you have a negative z minus z sub 0. And all of it equals 0. So that will be the equation of a plane when you have two variables. So pretty much the same thing. The only thing that you need to realize that here we have -1. Okay. All right. I'll give you an example, and I'll show you how to find the normal line as well. But if you think about what will be the normal line, well, normal line is in the same direction as the gradient, isn't it? So how we find, well, you have, remember that function that we find a vector in the direction of a vector v. You have a vector r, a certain surface that's described by, let's say, r of t. So you pick up a point and you call it, okay, this will be the position vector r sub 0. And you want to know what happens if you have, you want to create another vector in the direction of, let's say, v. So it's r sub r of t becomes r sub 0 plus t v. And that's how we're going to find the normal line. So the example will demonstrate that. So in this example, we need to find the normal, the tangent plane and the normal line to the surface x squared plus y squared plus z squared equal 30 at the point 1, -2, and 5. So we have two things to find, well, but in any event we need to find the gradient vector. So we set up a function here, f of x, y, z equals x squared plus y squared plus z squared. And this is in general. The surface level is when this equal to 30. But we don't care about that because when we take the derivative, it will go to 0 anyway. And what is the gradient of the surface to the surface? So the gradient vector del f of xyz in general is simply 2x plus in the I direction plus 2y in the j direction plus 2z in the k direction, or the vector 2x, 2y, 2z, which has the same direction as x, y, and z. Okay, so what happened at the particular point where we have 1, -2, and 5? Okay, now that the gradient become the following. 2 times 1 is 2, 2 times -2 is -4, and 2 times 5 is 10. So this is the gradient vector, 2, -4, and 10. So what is the tangent plane? Well, we have a simple equation to the tangent plane. At 1, -2, and 5 is given by. So what will be the equation? Well, the first direction number will be 2, the second will be -4, and the third will be 10. So we'll have 2 times x minus x sub 0, x minus 1, minus 4, the second direction number y minus -4, so that becomes y plus 4. Yeah, y minus -2, I'm sorry, I don't know why I said 4. Y plus 2, and then 10, the last direction, z times z minus 5. And all of it equals 0, and there you have it. So it's a quicker way to find the equation of a tangent plane than before. Remember what we had to do before: find the tangent, find the normal vector, and then come up with this. But the gradient gives you the direction number of a plane right away. I'm sorry?
So much better.
Yeah, it is. It is quicker. The gradient is muy importante. I mean, it's really this is you'll see it later down the road. That a lot of stuff. What was the derivative in a single variable calculus is the gradient in the multivariable calculus. All right. What about the equation of the line? Okay. So what would be the normal line? Normal line is given by, so we have some vector r of t. It's equal to the vector r sub 0 plus t and v. This is the general form. I mean, that's how when we learn this thing, that's how we learn it. So what would be in this case? In this case, we're going to pick up r sub 0 is the position. So it's the vector from the origin 0, 0, 0 to the point 1, -2, and 5. So the position vector will be 1, -2, and 5. Okay. What will be v? Well, v is the gradient, because we know that the gradient is the direction. The gradient is orthogonal to the plane, and the tangent plane. We are looking for a normal line, so it will be parallel. So we have what are the gradient is 2, -4, and 10, like so. Okay, and all we need to do is write. Here's the equation of the normal line. It will be 1 plus 2t, and then we have -2 and minus 4t and 5 plus 10t. Okay, so this is the equation. What will be the parametric and the symmetric equation? I didn't write it as a requirement. So parametric equation PE. Remember what PE stands for? Not physical education, but PE, parametric equation. Well, we have x equals 1 plus 2t, y equals -2 minus 4t, and z equals 5 plus 10t. But what about symmetric equation? Remember those? We solve for t and say t equals this and that. And the way it works is it will be x minus the point 1, the x sub 0 divided by the direction number, where the direction number is 2. And then it's equals to y minus y sub 0, which is negative 2. So y minus negative 2 becomes y plus 2. The direction here is negative 4. And finally, equal to z minus 5. Z sub 0 is 5 divided by the direction number, which is 10. And there you have it. So all three forms: the vector, the normal line as a vector, the normal line as parametric equation, the normal line as symmetric equation. Okay, I think I'll stop here. We have a couple of minutes, but it's not